All right. Good afternoon. Any question before we start the class? All right. We are talking about static failure theories. We cover 3 failure theories for ductile material. So those 3 are maximum shear stress theory, 2 distortion energy theory, and 3 is the Clomore theory or CMT. So on the first one, it says tau max when it's equals to SSY, which is the shear yield strength, we are going to have failure. Second one says when 1 says stress equals to SY, we have failure. This is the failure criteria. And this, on the Clomore theory, it says when we have the left side equals to the 1, we are going to have failure due to the Clomore theory for ductile material. If you want to incorporate the factor of safety, it's going to change to this. And what would be the ST and SC? Later on, you will see when I'm going to talk about the brittle material, the second failure theories that we are going to cover for brittle material, it's called brittle Clomore theory or BCM. Where it's going to be same as this, but ST is going to be ultimate tensile and SC would be ultimate compressive. Ultimate compressive strength. And this is going to be ultimate tensile. But where we have ductile material, ST would be SYT yield strength for tensile, and SC would be SYC yield strength for compressive. So comparing ductile and brittle material, just the strength term would be different. If we plot the failure criteria on 4 quadrants, where we have plane stress, then sigma A and sigma B, plane stress. It's gonna look like this. If this is SYT, SYC, negative SYC, and SYT, it's gonna look like this. It's similar to the maximum shear stress theory, except on the first one, SYT and SYC would be the same. So So this line, it's gonna have 45-degree angle or a slope of 1. Something like this. Sy, negative Sy, Sy, negative Sy. So this is the difference between these two. We work on one example. So today I'm gonna start with this example. Any questions so far about the failure theories before I go to this example? All right. So we have this component with the force of F applied at location D. So all dimensions are given, 15, 12, the diameter is given. So here we have a smaller part on the last 2 inch of this level we are going to have the larger diameter. So we know that this level is going to be strong enough to support the load. But the question is based on this size and dimension, what would be the maximum allowable force? What would be the F max which is allowable? Or how much you can increase the force before the yielding it's gonna stop. So we are looking for that force. So what would be the maximum force that you are allowed to apply to point D before the yielding initiate? So this is what we want to do. So if we want to do that, first of all, we should find the critical section. Where do you think it's going to be the critical section? On component OC. O is going to be on the wall, it has been fixed, and C is going to be the point at this joint. Find the critical section first. Where it's going to be the critical section?
At A.
At A. Why is that?
You're having pretty much all the forces going through that point, and it's necking down to a thinner diameter.
Okay. Point A definitely is going to be one of our candidates because it's going to have the smaller diameter. We should check that. But also point A should be checked because it's going to get more moment and the torque. Because this force.
Wait, which point should
Do you
also be
mean
checked?
also O?
Point O. It's
Oh,
gonna
okay.
Sorry, you said point A again. I was like,
sorry. Point O and point A would be our candidates. We should check both because one point or one section which is here, it's gonna see the smaller diameter which provides the larger stress. The other point, it's gonna see the larger moment and the torque applied to that section. We should check which section is gonna see the greater stress tears. Does it make sense? So there are two possibilities. So let me start with section A. Section A. What would be the load applied to section A? This force has a distance of 12 inch plus 2 inch, 14 inch in x direction. So this force times 14 inch is making moment about which axis? Z axis. This force is in y direction, the distance is in x direction, the moment should be on the other direction. Or you can imagine it's when you push force here, it's gonna rotate handle AC in Z direction. So MZ at section A. MZ is gonna be 14 times F. This force has distance of 15 from section A. So force times Z, it's making about x-axis. So 15 times F is making moment about x-axis. So the transfer shear, the transfer force, the shear force is going to be in this direction. Usually we neglect the transfer shear. I'm not going to look at it, but I can do that. So I'm just writing the V equals to F. It's a shear force applied to section A. There is no other force or load applied to section A. MZ, the axis of this component is x-axis. MZ has a different direction than the axis of this component, so it's going to be the bending moment. So 14F is going to be bending moment. This X is going to be same as the axis of component. It's going to be the torsion or torque. So this bending moment is making sigma or normal stress 16. Since the diameter it's going to be 32. Sorry, 32 mz divided by pi e power 3. How did I get this? mz c divided by iz. C is d over 2. Iz is pi d power 4 divided by 64. I'm gonna get this. So 32 mz divided by pi d cubic. So 32 m is 14f. Pi diameter is 1 inch. It's gonna be this. I will get 142.6 f. This bending moment is making this normal stresses. The goal is finding the F or the maximum allowable stress. Shear stress due to the torsion is going to be T C divided by J, or 16 T divided by pi d power 3. The torsion is 15F pi times 1 cubic. It's going to be 76.4 times F. These are the stresses applied to section A. This stress and this stress. Or at section O, which is the other candidates. MZ, the distance is gonna be 14 plus 2. 14 from point C to point A, and 2 inch from point A to O. It's gonna be 16 times F, and T or torsion or MX is gonna be the same, 15F. So the normal stress is gonna be 32. MZ is gonna be 16F, but diameter is larger, which is pi times 1.5. Not 1 inch, it's gonna be 1.5 inch. It's gonna be 48.28 F. And shear stress is gonna be 16 times T, which is 15F, divided by pi 1.5 cubic. It's gonna be 22.63 F. Make sense? So now compare these two. I mean, here both bending moment stress and shear stress for section A are larger than section O. So without looking at the principal normal stresses, I can say that critical section would be section A. I didn't count stress concentration factor because we have ductile material and we don't have fatigue problem. If it was made of brittle material, I had to consider factor of stress concentration factor for these two, which they occur at section A. And if we had dynamic loading, if the load was varying with time, then I had to look at stress concentration factor, but it's out of the scope of this example. We will look at it on chapter 7. So since these two both are greater than this, I don't need to find sigma 1, sigma A and sigma B and compare these two. But if one of them is greater, the other one is smaller, you have to find these two and then decide about the critical section. So now I'm gonna do the design based on this. Let me start with maximum shear stress theory. Maximum shear stress theory says tau max equals to SSY, which is SY divided by 2. Tau max is sigma 1 minus sigma 3 divided by 2 equals to SY divided by 2, or sigma 1 minus sigma 3 equals to SY. This component is made of AISI 1035 with yield strength of 81 kpsi. So the yield strength is 81 kpsi. It's given. I should find sigma 1 and sigma 3 based on this shear stress and the normal stresses. Plug in here and find F. How can I find sigma 1 and sigma 3? First, I should find principal normal stresses. Sigma A and B would be sigma x plus sigma y divided by 2 plus minus sigma x is 142.6 F, sigma y is 0, $76.4. $142.6 F divided by 2 it's gonna be 71.3 f plus and minus inside the square root. It's gonna be 104.5 f. So sigma A would be 175.8 times f. Sigma B would be negative 33.2 f. Negative 33 and 175. Any question so far? All right. Now find sigma 1 and sigma 3. We have plane stress, so we have sigma A and sigma B. The last one is going to be 0. So compare this, and 0. Sigma 1 is going to be the greatest force with the value, so it's going to be positive. 175.8 is the largest. Sigma 2 is going to be this, and sigma 3 is negative 33.2 times f. Apply this 175.7, 175.8 f minus 33.2 f equals to 81 psi, 81,000 psi. So F would be 81,000 divided by summation of these two. 175.8 plus 33.2 is going to be 209. Summation of these two is going to be 209 times F divided by this. I will get 388 pounds. So based on maximum shear stress theory, the maximum force that you are allowed is 388. Since it's made of the material with the same yield strength for the tensile and compressive, I can use the maximum shear stress theory or distortion energy theory or Coulomb theory. But if it was made of the material with different yield strength, I only can use Coulomb theory. So let me apply distortion energy theory as well. Do you expect to get a force larger than 388 or smaller than 388 for distortion energy theory?
Larger.
But it's a more conservative for this, so I should get larger allowable force applied to this. So for this, I should check this. One me says set it equals to SY. One me says either use these two, because we could find sigma A and sigma B, or use this one, sigma x squared plus 3 tau xy squared 1 over 2. Sigma y is 0, so the only term left on this is going to be sigma x squared plus 3 tau x squared. or use the other one. It's going to be sigma A square minus sigma A sigma B plus sigma B square square. It's easier for this case. Sigma X is 142.6 F. Tau XY is 76.4 F. If I plug in there, I will get 195 point F. You should get the same result. So 195 point F equals to 81,000. So F would be 81,000 divided by 195. It's going to be 416 pounds. So there is no right or wrong answer for this problem. So if you want to be more conservative on your analysis, you shouldn't apply any force greater than 388. If you want to be less conservative, you can apply up to 416 pounds. Makes sense? So again, as you see, the first step is find critical section and finding all stresses, finding all loads applied to that, and then find the stresses applied to that critical section, and then apply the failure theories corresponding to that material. All right, let's look at brittle material. If we have brittle material, there are three theories. The first one, it's going to be the maximum normal stress theory. We don't use that theory because it doesn't support the experimental data. We just introduced that. So one, maximum normal stress theory. MNST. It says you should find the principal normal stresses, sigma 1, sigma 2, and sigma 3. So the failure criteria is sigma 1 equals to S U, we don't have yield strength for brittle, UT, failure criteria, or sigma 3 equals to negative SUC. The failure criteria. Or we can say the failure occurs if sigma 1 is greater than or equal to SUT, or sigma 3 is less than or equals to negative SUC. Sigma 3 is going to be the smallest principal normal stress. if this is SUC, negative, negative SUC, and SUT for these four quadrants, if both sigma are positive, we will get this box, this is square. For this, we will get this. We will get this square. Inside the box is going to be the non-failure. Area outside of the box is going to be, we are going to expect failure. But on fourth quadrant, we will get some results in which this theory says these points should be safe, but the experimental says we have failure at these dots. So basically we cannot use this theory because it cannot predict the failure very well. We just introduced that to compare with the other two theories. So we never use this theory. The second one is brittle Coulomb mole theory, or BCM or BCMT. It's very similar to ductile Coulomb mole theory, which says sigma A over SUT minus sigma B over SUC equals to 1. If you want to incorporate the factor of safety, it's going to be sigma A over sigma SUT minus sigma B over SUC equals to 1 over N. SUT, SUC, negative SUC, and SUT. Tensile strength, they are positive. Compressive strength, which ultimate compressive. So on the first quadrant, where sigma A is greater than sigma B and both are positive. If this is the case, sigma 1 is going to be the greatest, which is sigma A, and sigma B, let me change it to sigma 1 and sigma 3. Please revise that. It shouldn't be sigma A and sigma B. It should be sigma 1 and sigma 3. Here, sigma 1 is sigma A, sigma 3 is 0. So plug in there. Sigma A divided by S ultimate equals to 1. This is 0. Or 1 over N if you want to incorporate factor of safety. You will get equation 531. Sigma A equals to S ultimate divided by N. So if I want to draw this line, sigma A should be S ultimate for tensile. It's going to be this. For quadrant 4, sigma A is greater than 0 and sigma B is less than 0 or negative. This is going to be sigma 1, this is going to be sigma 3. So the failure criteria is going to look like this. This line can be shown by this one. Similarly, I can do for quadrant 3 and quadrant 2 and I will get this failure criteria or region, which is gonna look like this. So depending on the loading that you have, you should use the corresponding failure criteria. If you find sigma A and sigma B and you end up somewhere here, both are positive and sigma A is greater than sigma B, so we should use this one. If you end up to quadrant 4, which is this case, you should use this equation. If you find point somewhere here. If you are here, somewhere here, sigma A is less than sigma B. Since these two are negative, sigma A is less than sigma B. So the factor of safety can be calculated like this. If your point is here, then N would be, then sigma A would be negative SUC divided by N, if this is the case. And for quadrant 2, you should revise this equation slightly by switching sigma A and sigma. Any questions so far? So this is number 2. Number 3 is called modified brittle flow mode or modified mortar, or we call it MMT. If you remember on ductile material, we had a theory, distortion energy theory, which could give us the better fit for experimental data. So if for brittle material we apply the experimental data for the failure, we can find some points if we apply different tests, we will get the different points and the failure occurs at this point. On the first quadrant, we can see we have a great fit between theory and the experimental result. Here, we have failure at this point, which can be expected by the theory because the points would be outside of the safe zone. But if we want to be less conservative, we are going to define the third theory. The third theory is going to look like this. If this point is negative SUT, if this is SUT, just put negative SUT, extend this line up to this point, and then connect this point to negative SUC. This theory is going to be modified more theory. It's a less conservative than this one, but it's going to have the better fit for experimental data. Similarly here, SUT here, negative SUT here, extend this line, and then connect this to this one. So the new safe zone is gonna look like this. That you can see here. The dashed line is gonna represent the Coulomb theory that I already talked about that. And the solid line is gonna be modified Moore theory, negative SUT. Just extend that line up to this point and then connect this line. Similarly on quadrant 2, if you extend the line up there up to negative SUT, then you can connect that point to negative SUC, you will get modified Moore theory. So quadrant 1 and quadrant 4, it's gonna 3, it's gonna be the same as before, but quadrant 2 and 4, it's gonna be slightly different than Coulomb theory. Any questions so far? I'm gonna talk about failure criteria for modified Moore theory. For modified Moore theory, if we are on quadrant 1, I'm gonna use the same thing that we had for brittle Coulomb theory. The only difference would be quadrant 2 and quadrant 4. Let me talk about quadrant 4 first. If I draw this line, which has 45 degree or a slope of -1, it's gonna pass through this point because this point has negative SUT and positive SUT. Any point above this line in this region, it has sigma A over sigma B, absolute value is greater than 1. Any point in this line is gonna see sigma A equals to sigma B because it's a line with the 45-degree slope. But any point above that line is gonna have sigma A greater than sigma B, absolute value. So if sigma A is positive and sigma B is negative, it means we are on quadrant 4. And absolute value of sigma A over sigma B greater than 1, meaning we are on the top of this line. Then we should use this line as a failure criteria. Equation 5, 32a. Sigma B over sigma A is less than 1. So sigma A over sigma B greater than 1, meaning this should be less than 1. If this is the case, we are using equation 5, 32a. Sigma A would be SUT divided by N, if the point is somewhere here. But if sigma A is greater than 0 and sigma B is negative, and sigma B over sigma A is greater than 1, meaning the point is going to be below this line, then we have to use this line as a failure criteria. What would be the equation of this line? Equation 532b. Minus sigma b you see 1/n. So the factor of safety can be calculated by this equation. If you don't want to incorporate factor of safety, just put it equals to 1, you will end up to equation of this line. So depending on where you are, you should use the corresponding equation. If both are negative, we are here, and sigma A is greater than sigma B, we are going to use that criteria for factor of safety. Same thing here. I didn't write the equation, but if you extend this line in this region, sigma A is positive, sigma B is positive, sigma A is negative. If we are here, meaning somewhere here, and sigma B over sigma A, absolute value, is less than 1. If we are here, sigma B divided by sigma B divided by sigma A is less than 1, we are going to be here. Then we are going to use equation 532A. But if we are somewhere here, then we are going to use this line. Just change sigma A to sigma B and sigma B to sigma A. We are going to use this equation. So this is what you need to know about these 3 failure theories. On Wednesday, I'm gonna work on 2 examples, which is covering all 3 theory for brittle material.